Hello, I am Dheeraj. Welcome to my channel. Imagine you ask a customer support chatbot, how do I reset my password for an app? A traditional large language model might hallucinate like, to reset your password, go to the settings tab, click password reset and enter your current and new password. But the company never had a password reset option under settings tab. Now, imagine a smarter assistant. It checks a knowledge base first, finds an updated company policy about password reset via email, and only then gives you correct answer. That is the magic of Retrieval Augmented Generation or RAG, a hybrid AI approach that combines information retrieval and text generation to create factual, context aware responses. RAG systems are powering everything from enterprise chatbots and AI copilots to legal assistants and medical support tools. But as these systems grow in complexity, evaluating them becomes a serious challenge. So, how do we know if a RAG model is good? Is it about accuracy, speed, faithfulness, or user satisfaction? Let's explore the top 12 metrics that truly matter when evaluating RAG systems. I will also demo using Python code and show how to measure these metrics in practice. Before going into evaluation of RAG, let us quickly discuss few fundamental concepts. At its core, a RAG system works in two main steps. Retrieval. The system fetches relevant information from a document store, vector database, or external API based on the user's query. Generation. The language model uses that retrieved information to generate a coherent, contextually grounded answer. So, instead of relying solely on its pre-trained knowledge, the RAG system can augment its responses with up-to-date and domain-specific data. Now, let us have a quick overview of each step in the retrieval augmented generation pipeline. The first step is to vectorize the documents. Vectorization converts each document or text chunks into numerical vector embeddings using a pre-trained model like sentence transformers. These embeddings capture semantic meaning, so similar texts are close in vector space. Then comes the user query. A user asks a question or makes a request in natural language. This query becomes the starting point for retrieval and generation. After that, we need to embed the query. The user's query is transformed into an embedding using the same model as used for embedding the documents. This ensures both query and document vectors exist in the same semantic space for comparison. Then retrieve the top K documents. The system computes similarity, for example, cosine similarity between the query vector and document vectors. It then selects the top K most relevant documents to provide factual grounding. Then we need to combine context. The retrieved documents are concatenated or summarized into a single context window. This context is appended to the user's query and fed into the generator model. Finally, generate the answer. The language model, for example, GPT, Llama, or Mistral, uses the context to craft a grounded, coherent response. The output combines retrieved facts with natural language reasoning to produce the final answer. Here is the simple explanation of the four main advantages of RAG or Retrieval Augmented Generation architecture. Reduced hallucination. Large language models or LLMs sometimes make things up when they don't have the right information. This is called hallucination. RAG minimizes hallucination by letting the model retrieve real facts from a trusted knowledge base before generating an answer. For example, instead of guessing the latest company revenue, the RAG system searches company reports and uses verified data, leading to more accurate responses. Better factual grounding. Traditional LLMs rely solely on what they learned during training, which may be outdated. RAG ensures responses are grounded in retrieved evidence, meaning every answer can trace back to actual text snippets or documents. This grounding increases trust, and users can verify where the information came from, similar to citing sources in research papers. Domain adaptation. A base LLM may not know much about a specialized field like medical imaging or banking regulations. With RAG, you can inject domain specific knowledge dynamically by connecting the model to custom datasets or enterprise knowledge bases. This avoids expensive fine tuning. Your model instantly becomes expert in any topic as long as it can retrieve relevant documents. Explainable outputs. RAG naturally provides transparency and traceability because it can show the sources it used to generate a response. When a model answers a query, it can list or link to the documents it referenced, making its reasoning visible. This helps build user trust and make RAG ideal for regulated industries where explainability is critical, such as finance, healthcare, and law. RAG matrix can be divided into retrieval part matrix, generator part matrix, and end-to-end matrix. Let us start with the four retrieval part matrix first. MRR or mean reciprocal rank. MRR measures how high the correct answer appears in the ranked list of retrieved documents. If the correct document is ranked first, the score is 1. If second, the score is 1 by 2. If third, then the score is 1 by 3, and so on. It rewards systems that put the right answer as early as possible in the retrieved results. For example, if you Google Python list comprehension and the first link is correct, that is an MRR of 1. If it appears in position 4, that is 1 by 4 is equal to 0.25 MRR. nDCG, Normalized Discounted Cumulative Gain. nDCG measures how relevant all the retrieved documents are but gives credit to documents ranked higher than lower ones. It uses a discount so that a correct document at rank 1 gets much higher weight than at rank 10. It is great when documents have graded relevance. For example, highly relevant, somewhat relevant, and slightly relevant. For example, when Spotify recommends songs, nDCG rewards the system more if your favorite song appears in slot 1, not slot 8. Precision at K checks how many of the top K retrieved documents are relevant. It ignores the rest of the ranking and looks only at the quality of the top K results. It is useful when the LLM only uses a small number of retrieved chunks, such as top 3 or top 5. For example, if your top 5 search results contain 3 correct documents, precision at 5 is equal to 3 by 5, that is equal to zero point 0.6. Recall at K measures whether the system was able to retrieve all possible relevant documents within the top K. It answers the question, did we fetch everything important the model needed? High recall is crucial when missing a key piece of information can cause hallucination. For example, if there are 4 relevant documents in the whole database and your system retrieves 3 within top 10, recall at 10 is 3 by 4, that is 0.75. Now, let us discuss the 5 generator side metrics. BLEU stands for Bilingual Evaluation Understudy. BLEU measures how similar the generated answer is to a reference answer using exact word overlap or n-grams. It rewards models for using the same wording as the reference, which is why it is commonly used in machine translation. It is strict. Small wording changes can reduce the score even if the meaning is correct. For example, if a machine translated sentence uses the exact words, you would get BLEU high. ROUGE stands for Recall Oriented Understudy for Gisting Evaluation. ROUGE measures how much of the important content from the reference answer appears in the generated answer. Unlike BLEU, ROUGE cares more about coverage of the key phrases rather than exact word accuracy. It is widely used for summarization because it rewards capturing the main ideas even with different wording. For example, if your summary includes all the important points of the article, ROUGE score is high. METEOR stands for Metrics for Evaluation of Translation with Explicit Ordering. Meteor measures similarity, but it is more flexible than BLEU because it considers synonyms, word stems, and paraphrasing. It penalizes incorrect word order but allows more natural variation in how sentences are written. It often correlates better with human judgment than BLEU because it cares about meaning, not just exact words. For example, if you say kids instead of children or buying instead of purchasing, METEOR still gives good credit. Perplexity measures how well a language model predicts the next word, where lower perplexity means better fluency and confidence. It does not compare against a reference answer. Instead, it evaluates the model's internal consistency and linguistic quality. In RAG, lower perplexity generally means the answer is more fluent and coherent. For example, if a sentence sounds natural and predictable to a human, perplexity is low. Awkward sentences have high perplexity. BERT score uses embeddings and semantic similarity rather than word overlap, making it robust to paraphrasing. It checks if the generated sentence and reference sentence convey the same meaning even with different words. It's currently one of the best metrics for semantic evaluation in RAG because it reflects true understanding. For example, if the model says the patient has a mild fever instead of the patient is slightly febrile, but score is still high because the meanings match. Now it's time to discuss 4 end-to-end RAG evaluation metrics. Groundedness measures how much the generated answer is backed by the retrieved documents. It checks whether every statement can be traced back to the context, ensuring facts come from evidence, not from model's imagination. High groundedness means the answer is anchored to the retrieved knowledge, which is crucial for safety critical domains like healthcare or finance. Faithfulness evaluates whether the answer accurately represents the source information without twisting, misinterpreting, or adding unsupported claims. It is more strict than groundedness even if the answer uses retrieved information. It must logically match what the documents actually say. High faithfulness means the model is not distorting facts and is sticking to the evidence exactly as presented. Answer relevance measures how well the generated answer directly addresses the user's question. It checks if the response stays on topic, avoids unnecessary information, and focuses on what the user asked. High relevance means the model did not drift away and provided information that is useful, focused, and aligned with the query. Hallucination rate measures the percentage of claims in the answer that are not supported by retrieved documents or contradict evidence. A high hallucination rate means the model is inventing facts, misinterpreting the context, and adding external knowledge incorrectly. For enterprise RAG systems, reducing hallucination rate is critical because hallucinations can lead to wrong decisions or legal or financial risks. If you are interested in exploring more concepts about machine learning, data science, and large language models, please find the links in the description of this video for more concepts, questions, and answers like this. Let us see a Python code demo for calculating each of the discussed metrics. Jupyter Notebook is up and running on your screen. The code for mean reciprocal rank computes how early the correct document appears in the ranked retrieval list. For each query, it finds the position or rank of the first relevant document. It then takes the reciprocal or 1 by rank, giving higher scores to documents ranked earlier. Finally, it averages these scores across all queries to get the overall MRR value. The code for nDCG measures how well ranked the retrieved documents are based on their relevance scores. It computes DCG, which gives higher weight to relevant documents that appear earlier in the list. Then it computes IDCG, the ideal ranking, and normalizes DCG by it. The final nDCG score ranges from 0 to 1, where 1 means perfect ranking. The code for precision at k measures how many of the top k retrieved documents are relevant. It looks only at the first k items in the retrieval list. It computes the intersection between retrieved at k and relevant documents. The score is relevant retrieved in top k divided by k, showing accuracy of top results. The code for recall at k measures how much of the relevant information is found in the top k results. It checks how many relevant documents appear among the first k retrieved ones. The score is relevant retrieved at k divided by total relevant documents. High recall at k means the system retrieves most relevant documents early. The code for BLEU compares a generated sentence to a reference sentence. BLEU measures n-gram overlap. For example, 1 gram words, 2 gram pairs, etc. Higher scores indicate the generated text is closer to the reference. The code uses NLTK's built-in BLEU function for simplicity. The code for ROUGE measures how much the model output overlaps with the reference summary. This code uses RUGE1, RUGE2, and RUGE-L by default through the RUGE library. Two text strings and returns recall, precision, and F1 score. RUGE is widely used in summarization and text generation evaluation. METEOR improves upon BLEU by using synonyms matching and word alignment. The code for Meteor compares the candidate response against reference sentences. The score considers exact matches, stem matches, and synonyms. It returns a value between 0 and 1 indicating semantic similarity. Perplexity measures how well a language model predicts text. Given a negative log likelihood and number of tokens, the code computes math.exponential negative log likelihood by tokens. Lower perplexity means the model is more confident in its predictions. This code uses a sample negative log likelihood value to illustrate the concept. BERT score computes semantic similarity using contextual embedding, not surface words. The code compares candidate and reference sentences using BERT. It outputs precision, recall, and F1 score based on embedding similarity. F1 score is typically used as the main quality score for generation. Groundedness checks whether the answer is directly supported by retrieved documents. The code splits the answer into sentences and sees how many appear in the context. It computes the ratio of supported sentences to total sentences. Higher groundedness means fewer hallucinated or unsupported statements. Faithfulness checks if the model output contradicts the source documents. This demo code uses a sample rule, no not contradiction, but real system uses LLM judgment. If no contradiction is found, the answer is labeled faithful. Faithfulness ensures the reasoning stays true to the evidence. The answer relevance code measures how well the answer aligns with the question. It compares word overlap between question and answer. The score is common words divided by total question words. Higher scores indicate the answer is focused and on topic. Hallucination rate measures how many answer tokens are not found in the retrieved docs. The code tokenizes both answer and context into word sets. It counts tokens that appear in the answer but not in the context. The final score is equal to unsupported tokens divided by total answer tokens. A lower hallucination rate is better. It's time now to learn the best practices for RAG evaluation. We should combine multiple metrics. Relying on a single metric can give you a biased view of performance. Combining retrieval generation and user level metrics offers a balanced and holistic evaluation. We should use domain specific ground truths, tailor evaluation datasets, and reference answers to the target domain, for example, finance, healthcare. This ensures that accuracy and relevance reflect real world expectations rather than generic benchmarks. We should benchmark against baselines. Always compare your RAG model to simpler baselines like plain LLM or keyword search. This helps you quantify the true added value of retrieval augmentation. We should monitor real world logs, track user interactions, feedback, and query response quality in production. Continuous monitoring reveals blind spots and helps fine tune retrieval or generation pipelines. We should use human in the loop evaluation. Include expert reviewers to validate factual accuracy and reasoning of complex queries. Human judgment complements automated metrics, ensuring trustworthy and explainable outputs. If you are interested in exploring more concepts about machine learning, data science, and large language models, please find the links in the description of this video for more concept questions and answers like this. By measuring key aspects, retrieval precision, factual grounding, fluency, and user satisfaction, we can ensure RAG systems are not just smart but also reliable, fast, and trustworthy. In short, evaluating retrieval augmented generation systems goes beyond simple accuracy checks. It is about understanding how well the model finds, uses, and communicates knowledge. A good RAG model doesn't just generate, it justifies. Thanks for watching. I hope you enjoyed this tutorial and found it insightful. If you learned something new, please like the video, share it, and subscribe to the channel. Also, consider sharing your thoughts in the comments below. Please don't forget to subscribe for more interesting tutorials and the latest updates. For more interesting questions and responses like this, please follow the links in the description of this video.